everyone, my name is Kamakshi Jibhkate from team The Carboholics, and we are going to brief our research on carbon capture and storage with my team members Manya, Ishika, Koustubh, and Aum, and mentors Sneha, Niyati, Nitesh. We have covered risk mitigation strategies, monitoring and detection on carbon capture and storage. Carbon dioxide geological storage is one of the largest CO2 emitting sources. Still, there are some risks associated with its leakage that could cause danger. Our analysis reveals the need for long-term monitoring and strong predictive models to better understand the behavior of CO2 geological settling. Our research helps us to develop platforms to minimize risk and to use geological CO2 storage responsibly as a climate-friendly option. We are going to cover a brief introduction on carbon capture and storage, risks of CO2 leakage, mitigation strategies, monitoring and reduction, cost-effective techniques, frameworks and policies, and a short feature review. Introduction. Global warming has a very significant effect on Earth's ecosystem and is a serious issue needs to be addressed. The increase in the level of carbon dioxide, methane, and nitrogenous oxide in atmosphere is noticeably since the beginning of the Industrial Revolution. There are a number of potential geological reservoirs that can be used to store captured carbon dioxide. These include depleted and disused oil and gas fields, deep saline aquifers, and deep unusable coal fields. Also, renewables efficiency are some of the climate mitigation strategies. Technical and research to gain policy and public acceptance, wide-scale development are some of the challenges and future directions. Deep saline aquifers are estimated to be 60%. Depleted oil and gas fields are estimated to be 25%. Unminable coal seams are estimated to be 10%. The desert formations are estimated to be 5%. Risks of CO2 leakage. CO2 leakage poses several risks that we need to be aware of. So let me give you some brief overview of the risks associated due to CO2 leakage. Environmental risk associated with CO2 leakage destabilize regional ecosystems and is harmful to animals also. Then health risks are like respiratory issues, headache, dizziness, and nausea. Then fields may leak and CO2 injection can sometimes induce seismic activity, that is induced earthquake due to changes in subsurface pressure. Then contamination of CO2 in aquifers, etc. Monitoring and detection risks are associated when leaks go undetected and due to less data, it becomes hard to find the problems. Then economical risks are also associated, like it is costly to repair damages, affects real estate market, job losses, etc. Moving ahead, we have legal and regulatory risks in that CO2 leaks may cause fine and penalties. Leaks may lead to cancellation of public procedure. Then technological risk when operational failures occurs in industries which increase the leaks and missed leaks and false alarms, etc. cause challenges. Further, social and ethical considerations are also important, like risk assessment in assessing health effects. Then climate risks are also associated, like impact on biodiversity, methodological and technological obstacles. Leakage can cause constraints that might hinder carbon capture and storage.
Hello everyone, my name is Koustubh Choudhary, and as we know that there are several risks associated with the leakage of CO2, so there are several mitigation strategies for the CO2 leakage. One of them is storage site selection, in which we need to have a tight cap lock, have pore space and low permeability. Also, the geological stability, leakage pathways and the history of integrity of the formation must be reviewed at the time of assessment. There are several trapping mechanisms which help in immobilizing CO2. One of them is structural trapping, in which we need our cap lock to be impermeable, and there must be both lateral and vertical seals around the structural trap that helps in cutting off the leakage. Another one is residual trapping. In this type of trapping, CO2 rests in pore spaces that are small. Also, the capillary forces helps in immobilizing the CO2 in the formation. Dissolution trapping. In this type of trapping, the CO2 mixes with the formation water, which is liquid or gases that are naturally occurring in the geological formation. Another one is mineral trapping. It occurs when CO2 reacts with the minerals in the reservoir and generally forms stable carbon. To enhance the CO2 storage integrity, we need to enhance well integrity, which needs the use of best practice well designs and also materials that resist CO2 corrosion. We need to conduct rigorous testing during well construction and operations also. We need to have a continuous monitoring and track of CO2 concentration, pressure and movement using seismic imaging, satellite data and gravity measurements in the geological formation. We need to have a regulatory and social support also. We need to establish a strong regulatory framework for site selections, operations and long-term monitoring, and we also need to engage local communities so that we can build up the trust and also to have our transparency between each other.
Next topic is CO2 monitoring detection techniques in CCS projects, which are done to ensure safe and effective carbon capture and storage. Monitoring and detection are done by some factors taking consideration like safe storage site selection, leak detection and monitoring the movement of CO2. There are three key monitoring techniques like seismic monitoring, microflora and fauna monitoring, and surface and satellite monitoring. In seismic monitoring techniques, seismic waves are used to create subsurface images and detect pressure or any structural changes. There are three case studies which we have researched on, like the Wave 1 project, Sleipner project and Snowy project. This surface and satellite monitoring. Surface monitoring is done with the help of an instrument which is used to detect CO2 in soil and atmosphere to monitor leakage.
Similarly, satellite monitoring purposes to detect CO2 into surface deformation. There are also tracer gases for CCS whose applications are on multi-well projects. This graph attached related to satellite monitoring in the next slide as well. Microflora and fauna monitoring, whose key monitoring aspects are soil and sediment analysis and biogeochemical influence.
Cost-effective CO2 storage techniques. Depleted oil and gas reservoirs utilize existing infrastructure, lowering cost. They can also support enhanced oil recovery, generating revenue to offset CO2 capture and transport expenses. Saline aquifers provide large storage capacity with natural barriers that reduces leakage risks, though they require monitoring. Finally, basalt formation allows CO2 to react with minerals, forming stable carbonates for permanent storage. Together, these options make CCS a more powerful tool in climate mitigation. Regulatory setups and standards for CCS. Carbon capture and storage, or CCS, helps reduce emissions by capturing and storing CO2 safely. Global agreements like the Paris Agreement and standards like ISO 27914 and ISO 14064 guide responsible CCS practices from facility setup to accurate CO2 tracking. However, we face challenges such as building public support and establishing regional rules for CO2 transport and cross-border responsibility. Policy, legal, and financial consideration for CCS implementation. Successful CCS implementation needs strong policies, financial incentives like carbon pricing, and a clear legal framework to reduce risks for investors. Key legal issues include intellectual property, site jurisdiction, and liability for potential risks. International groups like the IEA work to standardize CCS regulations globally, helping drive responsible widespread adoptions.
We will discuss simulations involving enhanced oil recovery using carbon dioxide. EOR is a technique where CO2 is injected into an oil field to improve the recovery of oil and natural gas. Injecting CO2 into the reservoir increases its density and enhances the extraction of trapped hydrocarbons over time. Additionally, this process contributes to underground CO2 storage, which can help sequester carbon and potentially reduce atmospheric CO2 levels. Following this, we'll look into the pre-processing steps of CO2 reactions within this method. These simulations conducted using Aspen Plus software will help analyze and optimize the process by examining the behavior of CO2 under various conditions. Aspen Plus provides a comprehensive platform for simulating the chemical and physical process involved in EOR, enabling us to improve efficiency and evaluate environmental impacts.